Right, so for the recording, I'm David, coordinator of the Maths Learning Centre. If you've never seen me, then where have you been? This is a revision workshop for real analysis. I call it a workshop because I'm not going to give myself graces to call it a seminar. We're making it up as we go along here, and I'm going to just talk through the advice I have about trying to come up with proofs, especially ones involving an epsilon, which is pretty much the entire of this course. So I'm going to take the lead from the people here if they have any specific ones they would like me to do, because I need problems to work with. So
the last assignment question B and C.
Is it on these somewhere? Is it on there somewhere?
Oh no, this was the mid-semester stuff. That was the show that x to the 2n divided by 1 plus x to the 2n was not uniformly converging.
We could tell you the question if that's what you want.
Yeah, well, I just want a question to work from.
Okay, like sequence or the limit of something and prove that it's unique or something.
Okay, prove that the limit of a sequence is unique.
Yeah.
That's a classic.
Nothing I can do.
Okay, that's not too bad on the other screen. It's a bit small for the viewers, so I'll... Okay, right here. Alright, so I apologise now that this will not look fancy. It will not be not necessarily be the standard proof, and I may have to cross things out and go back. It's really what I'm making up right now. Okay, so hopefully it will emulate what will happen in your exam, only you'll be even better in your exam than I'm being now, having had the advantage of actually having sat through this course. I'm sure I did this at some point in the past, though in my defence, when I did it, it was real and complex analysis in one course. So.
Can I just ask I just thought about it. Maybe you can show us how to prove the fundamental theorems in a way we understand it.
Okay.
That will probably show up.
Okay. Remind me in a minute, because I do still want to do this. Right. So show that the limit of a sequence is unique. Okay. So I suppose since it concerns a sequence, I should give my sequence a name. So let okay. That's a good start. That's how we normally write sequences in this course, isn't it? Okay, yeah. Cool. And I want to show that the limit is unique. So that's already presupposing that it has a limit. So I just want to show that if I was able to find something else that I thought was the limit, then it would have to be equal to the first limit I thought of. So the easiest way to show that something is unique, if you know it exists already, is to assume that there's two of them and show that they're equal. That's the standard way of showing that anything's unique. So suppose that L and M are both limits of this sequence. Okay? And so my goal, somewhere down the bottom of the page, would be say, therefore L equals M. That's what I'm aiming for. Okay? So this is my general way of trying to deal with proofs. There is another way of coming up with proofs, which involves drawing lots of pictures, and then that you're supposed to have the proof come to you. But I find that most of the time having a beginning and a goal and trying to make them similar is the best plan. So at any stage when you're not sure what to do, the first thing you should try and do is say, well, is there a piece of information about this that I could use? And the first piece of information you should use is the definition. So what does it mean for L to be a limit of a sequence? What does that mean?
Distance between the sequence and the limit is less than epsilon, absolute.
Okay, so we're saying that given any epsilon?
Yeah.
Yeah.
There exists.
There exists an n, which is an integer, a natural number, such that the distance between xn and L is less than epsilon whenever n is greater than or equal to capital, so this should be a capital N. So that's our classic definition. And that's also true for M, but possibly with a different letter. Yeah? So let's just call it 1 and that distance between xn and M. It's a good start. Okay. And from this information, we are supposed to be able to conclude that L is equal to M. Alright, at this stage, now that I've written down the definitions, I'm going to draw myself some pictures, just to have a feel for what's going on here. So, there are many pictures I could draw, depending on how you think about sequences, and all of them are usually helpful. But some of them might be more helpful than others, so I might have to draw several. So, I'm not going to put it here, because this is my exam proof that it's supposed to be all nice and readable for the person marking my exam. So I'm going to draw some pictures on a different piece of paper. I'm thinking, okay, so here's my real number line, and here's my L, and we're saying that I've got this sequence of x's that gets closer and closer to L. It might not come from one side, it might jump back and forth on either side of L, but this will do. So I've got this sequence that, you know, it eventually ends up there at L. Okay? And then my concept is that if I pick an epsilon either way, if I make n big enough, I'm guaranteed to be inside that zone. So if m was some other number, and that same sequence was also going to m, well, that wouldn't work because there's like this distance that's between L and M. There's this gap. So if it's going to L, eventually, if epsilon was smaller than the distance between L and M, I wouldn't be able to go to M. So maybe I'm not going to show that L and M are equal. Maybe I'm going to show that if it's true for one, it can't be true for the other. That might work. Or I could show that if everything's close to M and close to L at the same time, then the distance between L and M would have to be really small as well. And that sounds fancier, like it sounds like nicer. Because the other one of saying, well, if it goes to L, then it can't go to M, just sounds like I would have to do them both, you know, without lots of generating. That doesn't sound good. So I reckon we're going to go, and actually, there's that triangle inequality, right? Triangle inequality is usually a good plan. So now, okay, so we have a strategy here that we can reuse to show that things are equal. You need to show that the distance between them is 0. That's a really useful way of showing things are equal, especially because everything in this is about distances. So let's just look at the distance between L and M, and that would be less than or equal to the distance between L and xn and xn and M. Okay. And we know that this is less than epsilon plus epsilon for n greater than or equal to n1 and n2. Yeah? Okay. So that means that the distance between L and M has to be less than 2 epsilon, no matter what epsilon I pick. So for any epsilon, the distance between L and M is less than 2 epsilon. And the only number that satisfies that is 0. Because it's less than, if epsilon was 0.1, it's less than 0.2, it's less than 0.02, it's less than 0.002, it's less than 0.0002. And I think it's okay to just say that the only number that satisfies that is 0. So for any epsilon, and just in my own head, I am actually going to add the statement here, for any epsilon, however small, just so that it's easier in my head to know why it's true. For any epsilon, however small, L minus M is less than 2 epsilon, therefore the distance between L and M is 0, therefore L equals M. And the limit is unique. I don't go on to the next page because this is nice that it fits all neatly on one page. So that was a however there. Sometimes just adding a few extra words like that, and I know they don't sound really formal in the maths, so you might not put them in your exam, but just to convince yourself that what you've said is okay, it's all right to add some of those less formal words to just make you feel better about it. So, because the point is, the reason that this is 0 is because that can be as small as I like. Okay. Oh, I did go on to the next page anyway because I had a picture there. Ah, well. So what were you asking about? Like proving one of something?
Fundamental theorem of calculus, part 1 or part 2.
Okay.
Yes.
Sorry?
Yes.
All right. Sure.
I think it's probably like show fundamental theorem of calculus or something.
Yeah. Well, we'll prove at the moment and see how we go. Okay. And ideally wish they actually called it part 1 and part 2 back in Maths 1B. Because what you call the fundamental theorem of calculus part 1 in your course in Maths 1B, it doesn't have a name. It's the theorem before the fundamental theorem of calculus. Anyway, so I'm just see if I've got this right. Fundamental theorem of calculus part 1 says that the derivative of an integral is what you started with. Like it says that if you define a function as a definite integral, then it is differentiable if the derivative is the function that it's a definite integral of. That's my way of thinking about it. So it says that does it have to be continuous?
No. Because we have proven with finite discontinuities that it's still equal.
I think usually if he does ask you to do a proof of it, he'll do it in a specific case where it's continuous because it's easier. So
It doesn't have to be.
no, it just has to be integrable. So,
Yeah, we have if the function from A to B to R is continuous, then you've got
then the function like f of x, which is defined as the integral from a to x of f of t dt. Does he use x's in both of them? Let me look at yours.
yeah, you've got written right is differentiable on AB.
And that function is differential on AB, and its derivative is this. Okay. Okay. So So that is what we're attempting to prove. So all proofs have a place to start and a place to end. Mine has two places to end. I have to be able to say somewhere along the road that it's differentiable. Sorry, on the screen. Somewhere along that it's differentiable, and somewhere a little further, or somewhere, or at the same time, that this is what its derivative is. So that means that I'm going to need to know the definition of differentiable, and possibly the definition of definite integral, but that might not be as important. I might just be able to use the properties of definite integrals. But I should at least know what they are, because they're probably important. But I have a feeling that the definition of this might not be as useful as just the properties of the integral. So, what is the definition of the derivative? Like of differentiable?
Limit exists.
The limit of what?
Lim x to x naught f of x minus f of x naught.
So we want... Just tell me if I'm doing this wrong. Yeah?
No, it has to exist.
Exists
That equals the derivative.
at all and actually that limit is equal to f of x 0. That's what we want to show.
But is it the difference between the big F and the small f from your integral? I mean, on the limit there?
Yes, because this is the function that we're attempting to differentiate,
Oh, okay, yeah.
and its derivative happens to come out to that.
Okay.
So normally you'd have little f and f dashed. But we want this, that means it's differentiable, and we don't just want that, we want this limit, when we figure it out, to come out to that answer. Because there's two parts to the fundamental theorem of calculus, part 1. So it seems reasonable that we should attempt to calculate that limit. Alright, sure. What? Okay. So, right, it seems reasonable we should attempt to calculate that limit. I'm not quite sure what's going to happen yet. My understanding of it in my head, in terms of the picture, may or may not help. So I'm just going to draw that now while I'm at it. So this is my picture. So far all of this may not end up on my actual exam. This might not be on the scribble paper. Or it is okay to say, I want this, and write it down before you start your proof. That's okay as well in an exam. And at least it knows, at least even if you never get to the rest of that question, you've shown that you know something. So it might make a difference between one grade and another. You know, especially because Nick's a nice person, so you know he's likely to say, oh, they've got like 64. Oh, but they proved that they knew what derivatives were. So yeah, I'll give them the other one. Okay. So excuse me. My picture in my head of the fundamental theorem of calculus is that you've got that's your little f, and there's your a, and there's your b. It's not technically even defined out here, but that's okay. And then that's your x, this is your t-axis. And the area up to here, that area is capital F of x, because it's the integral from a to x. And then the derivative of f of x is the rate of change of f of x as x moves. So if x moves by a little bit, you'll add a little tiny slice of area, and that slice of area is approximately the same as the height of this graph, which is little f of x. So that's x there. That height there is little f of x. And so the rate of change of f of x as x moves, this little area is a tiny bit of x wide. It's dx wide and it's fx high. So that area there, that little tiny slice of area, is f of x high and dx wide. And so that's the change in f. That's the change in capital F. And if I divide it by the change in x, which is dx, I get f of x. Magic. Yeah, so this is my very tiny change in capital F, which is a very tiny change in the area, is equal to the height times the very tiny change in x, and then I divide both sides by dx, and there it is. That does not constitute a proof, but that's my picture that I'm thinking of. So I'm thinking that I'm hoping that I'm able to just do this as the difference between f of x and f of x0, and this is my dx, the x minus x0, so let's just hope this works. Okay, so f of x minus f of x0 would be the integral from a to x of f of t dt minus the integral from a to x naught of f of t dt. Sure.
Why is that again? Sorry.
Sorry?
Why is that?
That's the definition of capital F.
Okay.
So capital F of x is defined to be the integral from a to x.
Okay.
And capital F of x0 is defined to be the integral from a to x0. So that's actually the definition from what we were told of what the fundamental theorem of calculus includes a definition inside it. It's saying if you define a function as an integral. So this is just raw from the definition of capital F. And then we should be able to use one of the properties of integrals, which would mean that this is the integral from x naught to x. Because, what's he call it? Like the interval separation
Union
thing?
property.
Sorry?
Union property theorem or something?
I'm not sure. I don't know what any of them are called. Is that what you think it's called? Everyone else?
Union property.
Union property? Yeah, I mean we've actually done it as a difference property, but it'll do. So we probably should have written this plus this equals that, but this will do. Okay. So we get that, and so that's good because that's my little slice in my picture, this little tiny slice here. Okay, so I've got my actual x and my x naught, they're separating that. And so then I'm going to have to divide this by x over x naught. Okay. Sorry, f of x. Okay, cool. Alright, so is there a theorem about average values? Excellent. What does this theorem about average values say?
There exists a C such that...
That's true. So there exists a C such that little f of c is equal to this number? Okay, so this is the average value of little f on x naught x. Yeah? Okay. Is there a thing about doing integrals backwards and it being negative?
Sort of just when define it this.
Okay. Because technically x naught could be less than x.
Yeah, in this proof here he's split it up into, so if x naught is less than x, then this, and if it's not, then you have a negative and we switch the...
Alright. I'll deal with that in a minute. I'm going to have to go and fix my proof. But it just occurred to me that the definition of an integral in this course is probably only defined for a number lower going to a number bigger. So we'll deal with that in a minute. So far, I should go back and fix this. So far, this only applies for x naught less than x. For x naught less than x. But we'll deal with that in a minute. Okay, so this is the average value of that on that zone. And then there's a theorem. It's called the average value theorem, is it? It says there exists a C between... Sorry?
It's just proposition number 52 or something. And it just calls them all propositions, basically. There's lots and lots of propositions.
You know, they become theorems after they're proved.
This one has a name, the average value theorem.
Okay. The average value says there exists a C between x naught and x. Is it strictly between, or is it allowed to be one of the two ends?
think it has to be.
With round brackets?
Strictly.
So you can see what I'm asking myself. I keep asking myself questions. Is it okay to write what I just wrote? And sometimes I'm going, probably dodgy, but it'll do for now. And sometimes it can't hurt. But yeah, it is. I mean, it wouldn't make any sense for it to be strictly to be at the ends unless your function was constant anyway. So I think that makes logical sense that the average value shouldn't be at either of the ends. Because think of an increasing function, the average value is totally not there. Okay. There exists a C. Well, that doesn't say that there exists a C. There exists a C such that f of C is equal to this average value. Okay. So what do we got? We've got f of x minus f of x naught over x minus x naught equals f of C. Cool. Nice. So that would be the height I drew in my picture before. I chose f of x to be that height, but technically there's a C somewhere in that little tiny width that has the correct answer for the average value. And then I want to show that the limit of this as x goes to x naught is f of x naught. So, but that's okay because C is between x and x naught, and so if x goes to x naught, since C is between x and x naught, C would have to go to x naught as well. Can I just write it in words? Do you think that's appropriate? So,
You can say by the mean value theorem, average value theorem.
I've already used.
If you take the limit to that, and that's basically the mean value theorem.
Okay. So, I reckon I can just say that as x approaches x naught, C also approaches x naught as C is between x and x naught. So therefore, now I'll go on to the next page. Therefore, f of C approaches f of x naught. Since f is continuous, that's important.
Is that just squeeze theorem? You put C between x and x naught, so f of C is between f of x.
But we need f to be continuous for that to work. It is the squeeze theorem, but yeah, you need f to be continuous because it could have a horrifying discontinuity at x naught that means it suddenly jumps, and even though C goes to x naught, f doesn't because it's got this weird crap going on there. So since f is continuous, it had to come in somewhere. I mean, technically we needed it to be continuous to be integrable in the first place, but this is more. Can't hurt to use it again. And so therefore the limit as x approaches x naught of f of x minus f of x naught over x minus x naught is f of x naught, which is what we were trying to show. Now the only problem would be what happens if x is on the other side, which I haven't really considered, so I might have to fix my argument. So let me just go back and see if I can fix it without having to write it again. So, because this average value thing isn't going to work if...
It's just the sign change and you're still between x and
Yeah.
x naught.
So, I reckon at this stage I needed to put a little bit more in my working just to show that this came out to the right answer. So
all we need if we change the limits of the integral that it goes to negative.
yeah.
Yeah, we did that.
Yeah. So, but we need to mention it somewhere, otherwise our proof isn't complete. So, I would say that probably, but this is still true, regardless of whether x is more or less than x naught. Possibly.
Isn't it a sign?
Yeah, where you put a
Sign
minus in.
different.
No, it's still true. It's just that it's already negative. It's just that minus is included in the answer. I don't have to put the minus written here in the same way that.
Yeah, because we changed the way it was written also.
Oh, I did.
Like we put the x naught up the top and then the x on the bottom. But
Just to
that's
feel-
where the, yeah,
just to
it's still
feel-
the same.
To feel comfortable about it, why don't we just flip everything? I mean, we can. This is still true because it's just backwards. But you're thinking that you flipped this because the union thing said that it had to go from x naught to a.
Yeah.
Just a second. I need to draw a picture. So we've already done this one, where it's round this way, and then you're doing this one. So we're saying the integral from a to x naught minus the integral from a to x is the integral from x to x naught. Yeah. But then if we flip this one and that one, if we flip this one, it'll become negative. And if we flip these ones, the minus will go away. So it still works. But do you think we have to include that in our proof? Or do you think you can just blithely say it still works?
Something in between those two things?
Similarly,
Yeah, I'd say similar.
Sneak in a without loss of generality something?
I guess this is the real issue because the average value just has to be positive. It has to be like the absolute value of those things. So you would need to flip that, which would make it minus, and then flip that, which would make it minus again, so it's all okay. Alright, so I'm just going to... So if in an exam you got to this point and you're going, oh crap, I haven't considered both cases, I would, if I were doing this, I would say, well, which is the first one we did. Yes, that makes sense. And then back here, so this is technically x is going to x naught from above, technically. And now suppose x is less than x naught. And then we could just do enough working and say from this point forward the working's the same. Yeah? Okay. That part's the same because I'm just subbing in exactly what the definition is. But that's from a to x.
X. So it's not.
Ah, yeah, you're right. This is all supposed to be from x to x naught, isn't it? And so this comes out from x to x naught. Yes. So just as a little diagram, just on the side. So we've got this integral from a to x minus the integral from a to x naught. Ah. Right. I've got it. I understand now. We're going to do this. We pull the minus out and flip them round, and then I can be absolutely certain, because of the way my diagram works, that this is minus the integral from a to x. Is that right? Got a to x naught minus a to x, which is x to x naught. Right. like that. Cool bananas. Okay, and then f of x minus f of x naught over x minus x naught is 1 over x minus x naught times minus the integral from x dt, which is 1 over x. Cool. And so from this point forward we can use the average value theorem the same as we did before. So by similar using average value theorem. The limit as x goes to a naught from below x naught so therefore the straight limit okay, cool. And if we're at one of A or B, we don't have to worry about the other side of the limit because it's okay. Okay, and that should be square. Alright, so you would probably still have got almost, or maybe almost full marks if you didn't consider both ends, or possibly the full marks in an exam. But in terms of proving things, sometimes you do have to go back and fix it because it doesn't cover all the possibilities. And I have had a slight advantage to you because I have to keep asking myself, am I allowed to do this? Was there a theorem to cover that? And you guys actually know all of that already, which means that you're at a disadvantage because you don't have to ask those questions. So I would say as a piece of advice is ask yourself those questions. Am I allowed to do that? Don't go overboard because otherwise you get into this paralysis and you never do anything at all. But there does come a point where you should just look at what you've done and go, do I have to fix anything? And it is okay to just put a big star and say, see note below, and fix that bit later. Okay, there are, people reading it understand that it might be hard to read, might be hard to write proofs in the right order in an exam. All right, do you want me to do another one? What one will I do?
Show part 2.
Alright. What does part 2 say?
Integral is equal to f of b minus f of a.
Okay, so if
The function in the interval AB going to R is differentiable. Small f.
does that say f inverse is integrable?
Oh, it's supposed to be integral. Hang on, I don't know. I wrote that. I looked at that.
Oh, and dash, f dashed. That's not f inverse, it's f dashed.
Giving rise to that, like.
Yeah, it should be dash. Yeah.
Okay, so the fundamental theorem of calculus part 2 says that you can integrate a derivative by the method that we're used to of integrating it and subbing in the two ends and subtracting. So part 1 says you can differentiate an integral, and part 2 says that you can integrate a derivative. Useful way of remembering it. And that's the proof, which I will attempt to avoid looking at. Okay. So it would seem to me that in order to show that an integral comes out to something, I would have to use the definition of an integral. So what's the definition of an integral?
One bounded function, there exists a partition such that the upper sums minus the lower sums are less than epsilon.
Okay.
That's a theorem.
That's the theorem.
That's a theorem. The definition is that the set of the limits for all partitions. I don't know how to say it in words.
Has someone got the actual definition? There's like a lim soup or something?
The largest lower sum is equal, the largest lower sum is equal to the lowest upper sum. If they're equal, then that's the
integral.
Now, the
common point.
The infimum of the upper sums minus the supremum of the lower sums.
For all partitions.
For all partitions.
For all partitions.
All partitions are less than epsilon.
Yeah, I'll try and
I haven't written it here.
just can't find it.
I'm saying words.
Alright, pass it to me.
So you upper and lower sums and then upper and lower sets.
Definition of the integral. Partitions.
If f is Riemann integrable, no, f is Riemann integrable if the supremum of curly L and curly L is the set of all lower sums over all partitions. Sure. Yeah. Is the infimum of curly U, which is the set of upper sums of all partitions. And if this is the case, then we define that to be one or both of those and call it the integral. Right. Okay, so I'm just going to keep this for a second.
That's why I remembered theorem.
And what does the theorem say?
It's effectively the upper sums minus the lower sums are less than epsilon. There exists a partition such that, and then you can go from there and say consider the infimum of the upper sums minus the supremum of the lower sums, and you can make that as close together as you want.
But that's not a definition of an integral.
No, it's a theorem.
They give up the
If
half.
So that's the theorem.
If and only if there exists a partition E, so
Yeah,
there's an
f has to be
epsilon.
integral
So it's
to do that.
yeah.
Let me see.
That second one there.
Alright, f is integrable on AB if and only if there exists an epsilon, for all epsilon greater than 0, there exists a partition of P such that that is equal to that. Right, but it doesn't tell you what the integral is, which is what we need.
Yes,
We need
it's
the
not
integral.
useful.
Yeah, we didn't do that.
There's not a theorem that says if it is integrable, then there is an upper sum that is equal to it. No, because it's a supremum, so there might not actually be an upper sum equal to that. That would only be if it was a maximum. Okay, cool. So I might actually look at the sheet and look at the proof, but the definition goes, so the definition goes that for any, so being integrable, right, let's give the integral a name. Let that be A. Now we can talk about it. It's got a name. Okay. Because we were told it was integrable, so it has an integral. So let's call it A for area, because that's what's in my head here. And so this A happens to be the supremum of all the upper sums. All the lower sums, sorry. Yeah?
Yeah, the sum of the lower sum.
Yeah, and it's also equal. It's also the infimum of all the upper sums.
Yeah.
Right. So therefore, no matter which partition I pick, its upper sum will be more than this. And no matter which partition I pick, its lower sum will be less than this. Okay. I think we may be able to use the theorem now. So the theorem says that for any epsilon greater than, so the integral will be A if for any epsilon greater than 0 there is a partition that makes something within epsilon of A. Is that what the theorem says?
Or the upper sum minus the lower sum of the partition.
Yeah, so
it's kind of similar to the definition of continuity. So basically saying if we squeeze the integral along.
Oh no, my thinking phase here is how do I make that work in my proof, not what does it mean. Sorry, no, I'm all good with it. Like the theorem says it's integrable if the upper sums approach the lower sums. That's what it says. It says that, you know, no matter how close together you want them to be, you can find a pair of them that are that close. But the problem is that that theorem doesn't specify how close it is to the actual answer. But since the answer is between them, the triangle inequality would say that since the distance between... No, it's the derivative inequality is the wrong direction. I'm going to just let me just...
You're a bit far off. Well, he's gone in a different direction.
I'm pretty sure you need that.
No.
What he's used, what he used.
Well that makes sense.
Need that.
Oh, we used the average value theorem to prove part 1 and the mean value theorem to prove part 2. That makes sense. No. Okay, but we still need a partition.
Yes.
Yeah.
I'm going to keep that because I want to compare what I'm about to do with it because it's not going to be the same. Okay, but we are going to need, so after all that discussion, whatever we do, the only way for us to talk about this in terms of the definition is to make a partition. We're going to have one in order to do this at all.
If we do that series, talk about integrals really.
If you're going to prove that something is integrable, you're going to need a partition. If you're going to prove that it has a particular integral and prove it, you're going to need a partition. Okay, so that's our general idea, because that's the definition involves partitions. And even the theorem that we had involves partitions. So we're going to make a partition, so there. Okay, so we've got A is x0, which is less than x1, which is blah, 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 which is less than... Okay, capital N. So in the other one, I had my x minus x0, and that was a small thing. And then when you do integrals, each individual piece, the function value is equal to the average value on a very small interval. Right. Okay, good now. So I'm going to pick one of the intervals, one of the sub-intervals. So on any okay, that sub-interval there. F is differentiable. Because f is differentiable, and therefore we can use the mean value theorem because it's differentiable on there. That's it, you know, which means it's continuous, so we can just do that. And so there exists a C in I. Such that f dash c right, it's the mean value theorem. So that's the mean value theorem. Okay. Cool. Happy with that? Okay. So what we really want to do, I'm just going to cheat, I'm sorry. I'm tiring now. I'm just trying to see where we're going to... Oh, we have to integrate this, don't we? This is what we have to integrate, the derivative. And then we have to times it by the delta x, and that's the delta x. And so the delta x is the distance between those. Right, and so we timed it by that. So that's going to give our f of x delta x. Right. Yeah. And so this is my... Okay, and that CI would be like an XI star that's somewhere in that interval. And then...
X minus 1.
Yes. Thank you. And then so... if I add them all up, now this will be one of the sums. It's not necessarily an upper or lower sum. This is one of the Riemann sums, which is guaranteed to be between any upper sum and any lower sum. So for this partition, so we've got. And this would be, it's a telescoping sum, so we only get one end or the other because we've got 1 and 0 and 2 and 1 and 3 and 2 and then n and n minus 1, and so we're going to get f capital N minus f of x capital N minus f of x 0. Which is f of a, b minus f of a, because that's what those things are. Cool. And so, no matter which partition we have, there is a Riemann sum on that partition which gives you this answer. Right? The upper sums are all more than this Riemann sum. The lower sums are all less than this Riemann sum. And so the supremum of the infimum of all the upper sums has to be less than or equal to this, greater than or equal to that, and the infimum of all the lower sums has to, the correct things are greater than and less than, and since they're equal, they have to be equal to that. That's the argument. But this will do. So we have, no matter which partition we have, where's the definition of the Riemann sums? We had it on one of your pages. I just want to be sure that I'm allowed to say this. Sure, there's like a theorem about Riemann sums.
Yeah, they're just definitions on that page.
What it is.
Integral a to b f of x dx equals the limit of the sum 1 over n of f of xi times delta x.
Okay. So that's what we need to look up for.
Yeah. So the formal definition would go something along the lines of the upper sum on this partition would be greater than or equal to any of the Riemann sums. Yeah.
Yes, any sum of the form sum blah 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 is called a Riemann sum.
Yeah.
But it's also smushed between.
No, because you can
I think he uses the mesh of the partitions as that approaches zero.
Yeah.
The Riemann sum.
The what?
The mesh.
Oh, the mesh. What is a mesh?
It's the largest spacing on a partition.
Ah. And is it just defined as length?
Yeah.
Yeah, but it's the max length of the interval.
As the mesh on the partition approaches 0,
Which is the maximum xi. The right-hand side approaches the integral, or the sum approaches the integral.
the Riemann sum approaches the integral.
Yeah. Because that mesh of partition is the maximum value of xi.
Yeah.
And so you get the exact definition.
And so since all of these are the same, and they're all equal to that, this has to be equal to that too. Yes. So i.e. f of b minus f of a approaches the integral. Therefore the integral is equal to f of b minus f of a. Sorry, I didn't know about mesh. Never heard of that before. So, yeah. Alright, so I was going to go down a different argument, which I think would have been just as good. But, you know, whatever. I was actually going to say, well, the upper sum on this partition is greater than or equal to that, and therefore greater than or equal to this. And the lower sum on this partition is less than or equal to that. And so therefore the infimum of the upper sum is greater than or equal to this. The supremum of the lower sums is less than or equal to that. And since they're equal to each other, they must be both equal to that. And therefore that's what the integral must be. So that's a different way of doing it. So, sorry? I'll write it down. Or, because the upper sum is defined as the supremum of all of those Riemann sums?
You take the largest value in each interval.
You take the supremum of each interval.
Yeah.
Yeah. But you still times it by the delta x and add them up, right?
Yes.
Or, the upper sum on P is greater than or equal to the Riemann sum. Which is f of b minus f of a. Therefore, the infimum of all the upper sums must be greater than or equal to this. Right? And the lower sum on P is less than or equal to because each of these numbers is less than is greater than its infimum, which is f of b minus f of a. So therefore the supremum of all the lower sums is less than or equal to f of b minus f of a, but inf u equals sup L as it's integrable, and therefore the integral must be equal to that number. So this number is less than or equal to that and greater than or equal to that. So just for completeness' sake. Is that nicer? I like it. Because that's a direct use of the definition of what the integral is. So, and if I had written that down and you were happy with it, I would never have known what mesh was. So perhaps, it was better that I didn't. Because now I know something more than I did before. Of course, in an exam, no one would have been there to tell me what mesh was, so I would have just done this. So we've already learned that there is more than one way of doing something, and it seems that your lecturer is okay with something that doesn't directly use the definition, unless he specifically says to. You're allowed to use one of the theorems somewhere. I never realised this at the time when I studied this, but I think it's supremely cool that you use the average value theorem to prove part 1 and the mean value theorem to prove part 2. Because the average value theorem is about integrals and the mean value theorem is about derivatives. Which is really interesting because part 2 is about integrals and we use the one about derivatives to do it. And part 1 is about derivatives and we use the one about integrals to do it. Wow. Anyway, but this one's about the integral of a derivative, and the other one's about the derivative of an integral, so, in the end. Anyway. Okay.
Can you draw it for me? Because that's how I sort of learn.
Yeah.
Can you show what the difference is between converging pointwise and converging uniformly?
So for a
Yeah, just draw a function and show, like, I know there was a good picture that you drew, but just show what the difference is. Like, do you want me to give you a function? And then you can draw it, and that will help me.
Sure. Okay, so can we just talk about what the definitions are, and I'll come up with something.
They're underneath each other.
So we have a sequence of functions. Yep. And it converges pointwise or uniformly. Okay. Converges pointwise. So that's saying that this function, this sequence of numbers, converges to this number for all x. Cool. So for each x separately, given any epsilon there's a delta, no, given any epsilon there is an n, so that beyond n we can get within epsilon of this answer here. Okay, I'm just talking it out so that I can get an answer. And converging uniformly okay, just before I put that in, I'm just going to say, so for each x separately, for any epsilon greater than 0, there exists an n in n such that the distance between f of x n and f of x is less than epsilon whenever n is greater than or equal to capital N. That's the definition of this sequence of numbers converging to this number. But the n might be different for every x. Okay, so just to point that out really clearly, there will be an n which is based on the x. Okay, each x has its own capital N. They might all be different. Okay. Converging uniformly. I think I may be able to, talking this through this way is giving me time to come up with a picture. It's also giving me a way of, if I talk about it in enough detail, I can come up with the right picture. So converging uniformly is for all epsilon there exists an n in n such that oh crap, that's the wrong n there. Sorry, I put the n in the wrong spot. It's not inside, it's on the outside. Is less than epsilon for all n greater than or equal to n and x in the domain. Okay. So the difference between these is this one we have that's the wrong n. For this, we have a single n that works for all the x's and this epsilon. And in this one, given a particular epsilon, all the x's have an n, but they're not necessarily all the same n. Okay, and we want a picture of this. So what we have is a sequence of functions. So there are multiple ways to think of functions. Functions of real numbers are easier than all other functions because they have an x and a y. So I'm going to draw that picture. But you can also think of them as before and after pictures, and that's harder in this sense, so I'm not going to do that. Okay, so we've got our domain, right? And we have a sequence of functions. So, just thinking. This might be F1, and then maybe maybe this is F2, and maybe this is F3, and so on. There's all these different functions. Okay, and they're hopefully all getting closer and closer together. Okay, so I might only look at this part of the domain if you don't mind. Yeah, that's my domain there. Okay, so the idea is that my functions all get closer and closer and closer to something. And that's my single f, my limit of the functions. It might be that I do other crazy crap over here, but on this domain it works, which is the whole idea of Taylor series. They might only work in a certain zone. And this is all in service of Taylor series anyway, that's the goal. Okay, so I'm going to blow up that, and I just needed to, this is going to take me a while to construct a picture. Okay? So they can do any crazy crap over here, but it's this part here I'm interested in. So I'm going to blow up that part of the picture and show it in more detail. There's my domain there, and I've got they are allowed to cross each other, but it's just easier to think about it this way. Okay, so my functions start here, they get closer and closer to this function here. So this function here is my f, this is f1, f2, f3, and so on.
So it's kind of like Cauchy being there over that domain, Cauchy for every x.
Yes, so you're actually making a Cauchy sequence for every x.
Yeah.
Okay, so, right. So converging point-wise means that at every x, no matter which x you pick, this x, you've got a sequence of y values. Okay, that are converging to this value here, which is f of f. And what we're saying is that however close we need to be to this, so we're going to have a zone, I'm going to draw it in green, I'm going to have my epsilon. They might not approach from below, they could actually, some of them could be above and some of them could be below. But it's easier to think about it below. Here's my epsilon, which follows my original function. That's my epsilon zone there, around my function that I'm hoping to get to. It's my epsilon zone. And I'm saying that, okay, so for this x here, maybe it's 1, 2, 3, 4, 5, 6. My capital N is 6, and it takes me 6 to get into that epsilon. And for this x here, 1, 2, 3, 4, 5, 6, 7, it takes 7 to get within epsilon. And maybe over here, they all bunch together much more closely in this way, and it takes 20 to get to within the epsilon. And so each x might take longer, okay? So you can imagine, what if they're all sort of really widely spread out on one end and really closely bunched together at the other? It would mean that you would have different ends for each x, okay? But if they're all sort of evenly spaced all the way along, you could imagine, well, maybe this one takes 10, this one takes 20, this one takes 40, but overall nothing takes more than 100 to get within that zone, so my capital N's 100 for all the x's simultaneously. Okay? Right. That's my picture. Okay, so in terms of the whole function at the same time, we're saying that there is an n so that the entire line is within the zone, all in one go, rather than just each of the points separately. So pointwise is saying, I'm just looking here, how long does it take to get into the epsilon zone? Just looking here, how long does it take to get in the epsilon zone? And there is one that gets there eventually. And now, rather than with uniformly, we're looking out and we're saying, is there an n so that the whole curve is within the epsilon zone?
Yeah.
Does that feel good?
Yeah, that's a lot better.
Right. So, not converging uniformly, it's really difficult to think about, but you can imagine that maybe at one end it takes 10, and it takes 20, and it takes 10, and it takes 100, and it takes 1,000, and it takes 10,000, and the closer you get to here maybe, or some point somewhere in the middle, the higher the number gets. And no matter how big a number, you know, the closer you get, the higher the number gets, and there's never some upper limit. There's always another x that takes even longer. So if there's always another x that takes even longer for that epsilon, and you can never get to an n that's going to cover them all, then it doesn't converge uniformly. So it's really hard to come up with non-uniform convergence. But ln x does it. I have a feeling ln x doesn't converge uniformly like its Taylor series only works from 0 to 2. And it doesn't. I don't think it converges uniformly on that because it does weird crap down here at 0 and up there at 2. It does actually converge at 2, but I think that if you came into any zone small, that's my feeling. But there was an example in one of the assignments or tutes or something that didn't converge uniformly because you needed to. Each x gave you a different n.
X to the 2 over 1 plus x to the 2 and
Yeah.
negative 1, 1.
So it was like
1 plus x to the 2 over the open interval negative 1 and 1. And it was convergent on negative a half positive.
uniformly, yeah. So the concept is that given an epsilon, you want to show that there is at least one epsilon, so for which there's no n that works for all the x's. That would be not converging uniformly. And so you can say, well, given epsilon greater than 0, you could say, all right, I've got my epsilon greater than 0. I need to figure out the n beyond which my function value is close to whatever. And what was the actual f? Just a second.
The function that it's going to.
Converges pointwise to f is the 0 function.
Well, it just. Oh, it's a function. Yeah.
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 So that means that all of the sequences, starting with given x and doing the first function, the second function, the third function, they all go to 0. So in that case, the picture is that you've got all these functions and they flatten out and end up at the... and so you've got... I have no idea what that looks like, but you've got sort of all these functions and they flatten out and eventually end up on the x-axis. Yeah. So it's the 0 function.
Yeah.
Yeah.
Like x to the n without.
See, I just get so confused because they go from
Sequences
like,
of numbers and
yeah.
sequences of functions, and then the function has a sequence of numbers and... Wah!
My brain just gets a bit lost.
Okay, so that's our picture. And the idea is that it's really closely bunched together at one end and really widely spaced at the other. That's probably what's going on. So, in fact, the more closely bunched together it is down the bottom here, the harder it is to go and get an n to get into that zone. No, it has to be widely spaced here. Yeah, so it has to be, it's going to be closely bunched down at this end and closely bunched up at this end, and it's going to have all these spaces here. It's going to, yeah. The further you go, the more widely spaced relative to where you're up to it is. Okay, so I would say that what you want to say is that to not converge pointwise means that no matter what zone around here you pick, right? Here, let's get my epsilon zone. There's my epsilon zone. No matter what zone around there you pick, there is no n such that, given a particular epsilon, there is no n such that the whole of every function's line beyond there is within that zone. That's converging uniformly. So that means that every function, no matter what epsilon is, every function has a piece that's outside that zone. That's what that says. Some small part of it, even 1 point. Okay? Yes, they all have a different piece that's outside. Ah, yes, so that's it. So this was the point 1 at this end here. This end here had the point 1. And we're saying that no matter how close you got to that, there's always another function that's got a little tiny bit that's above here. Okay, that all the other functions are below, but it's almost as if they actually all have a converge to a point there, let's say. Actually, when x is 1, what do you get? A half for all of them? Yeah? Is that right? When x is 1, no matter what n is, when x is 1, the answer is a half. So what my function looks like is here is a half, and all of these functions actually like that. They get steeper and steeper, has a faster decrease here, steeper and steeper and steeper, but because they all go to a half, no matter which function you've got, it always has points that are above an epsilon zone. That's why it doesn't converge uniformly. Freaking awesome. Okay. Understand. That's really clever. And so, and then it becomes like a step function, doesn't it?
Yeah, because
and so the other side it'll go like up like that. And this gets closer and closer to that corner. But because all the functions have a piece that's near a half, you can, yes, okay, cool. That would actually have made the problem so much more easy, I reckon, if I'd thought about it that way. But what I did was I went, well, given an epsilon, I went, okay, so if it wasn't going to converge, if it was going to converge uniformly, there would have to be an n that worked for all the x's. All right? So if I give a particular x, I can figure out which n it takes to get within epsilon of 0, right? So, add x in the domain. I'm going to find nx such that is less than epsilon. Okay, because that's what I need to find to do the converging, right? And if I can find that across all the possible x's there is a maximum n, x, then I'll be able to find an n that works for all of them. Okay? But if I find that there is no maximum nx, there isn't a maximum nx, and there isn't going to be any n that covers all of them. So that's how I thought about it. Okay? So I went, okay, so I've got, so I just solved this equation. Yep. And both of those numbers are positive, so I can ignore the absolute values. Actually, I won't though, but I'll just bring them inside. Oh, I don't know, I'll just deal with that in a minute. My aim is to find n, right? Just to be clear. So I'm trying to get all the n's on the same side. Now, am I going to have to flip that inequality sign? If epsilon is really small, 1 minus epsilon is positive. Okay, so no. Okay? Because I'm just, I don't have to work for one epsilon, any epsilon at all will do. So, if epsilon is small, 1 minus epsilon is positive. So I don't have to flip my inequality sign. Okay. I'd have to do logs to get the 2n out of the power if I wanted to find what n was. Have I done everything right there? So let's see. I didn't know if this was the best plan when I did it, but it seemed to work. Whoa. What time are we up to? Okay. That clock is wrong.
2:32.
Heaps different when I did it on the assignment. I did a contradiction.
Oh, I'm sure there's any number of ways to do it.
Heaps differently.
But this is the first thing I thought of because of the picture that I had. X is less than 1, which means ln x is negative, which means we're going to have to flip the inequality sign. X is less than 1. Sorry?
Oh, yeah.
X is less than 1?
Yeah, no.
Which means ln x is negative, which means when I divide by it, I'll have to flip the inequality sign. Which is useful because I wanted n to be greater than something. Because I needed it to get bigger and bigger. Great. And so now I just need to be convinced that if I choose x in such a way that there is no n. So this is going to be my nx, right? If I choose my nx to be equal to whatever the nearest integer is to that, then that will be my nx that I need. So, you know. Alright, so nx is greater than or equal to whatever that number is. I probably could have done a different argument earlier, but you know, this is what was in my head. And so I'm going, okay, this function, as x goes to 1, this goes to 0, and so this increases as x increases. So ln x goes to 0 and x goes to 1. So as x approaches 1, this nx increases, so it has no maximum. So consider, you know, as x goes to 1, ln x goes to 0, and ln epsilon over 1 minus epsilon over 2 ln x goes to infinity. So in x has no maximum or even supremum.
Can you use the same argument since x is between -1, 1?
Yep, that's why, because we're going to 1. So we only need to work at 1, we only need to fail somewhere.
One. Yep.
Okay?
Yep, that's fine.
So it has no supremum that will work for all x, and so therefore has no supremum, and so therefore there is no capital N that will work for all x, and therefore it's not converging uniformly.
Yep.
So that's one way of going about it. There are other ways, but that's the first thing I thought of.
You haven't made that suitable for negative values to go into the LN.
Doesn't matter. Okay, so at this you're right to do the ln. I am, only. All right, let me just.
But you only need to fail at one point, and then you fail.
That's right. You only need to fail at for a particular sequence of x's. Okay, but if x is between minus a half and a half, mod x is limited. Like mod x is between minus a half and a half, and ln x is between a couple of numbers. So there is actually a maximum.
Yeah, but he doesn't like us doing it that way.
He probably doesn't.
He killed me in the assignment for part B
Yeah.
using that reasoning. So,
What's that for?
when for a half, they only give a half, it works, and I was slaughtered with that.
But you're right. If I was going to do it, if x was between minus a half and a half, I would actually have to probably look at that and go, that argument probably is a little less sure for a specific zone that I know. I would have to basically work backwards and let epsilon be something that made this work. Is that what he killed you for?
Yeah, he said I had to show that there was a specific epsilon.
No, there was a specific n.
Yeah, specific
So this is saying, so if I did have x was between minus a half and a half, this working shows that if n is greater than or equal to this, then it converges for that x, yeah? Okay, so let's just do that part. But if x is in fact between minus a half and a half, then ln mod x is between 0 and minus ln a half. Yeah, and my ln. Crap. ln mod x is between 0 and ln of a half. Right? Okay. And so therefore. Minus ln2. Not that it matters, but it just looks prettier. Okay, and so therefore we get that nx is greater than or equal to minus 2 ln2. Cool. Great. Right. So that's telling me that if I choose capital N to be greater than that, then it'll work for all the x's. So just to be sure, I should say, so and pick a number, right? To be that, basically. Yeah? Which is a perfectly good number. Well, the ceiling of that, I suppose, you have to have a whole number. Was there a specific number in his solutions that he picked? That's my number, though. The ceiling of that, because it has to be a whole number, right? So, can't just be that. What did you choose? I don't know. That's the number I choose. I choose you, Pikachu.
Yeah. And the way he took it is because that goes.
That makes sense. It works.
It's not dependent on x, which is what we need.
Yeah. You could probably talk it through and pick just like ln epsilon or something, because that'll work. Because ln2 is sort of like 60%.
Yeah, I think.
So it's dividing by that. You'd probably like choose like 5 ln e or something. ln epsilon. And ln epsilon is going to be close to 0. I don't know.
See, I solved it.
What number did he pick?
It got
He didn't pick a number.
Did he?
I think the solution.
Which is done for you.
Yeah.
Can I look? Just a tick.
Ticks up.
Oh, taking n to be sufficiently large. The supremum of that is less than epsilon. Oh, I get it. Okay, yeah. Well, this is what I did, but I don't know. So yeah, this is probably not the best plan. It's probably best to go back and go back to the beginning and say, well, I can make it as small as I need it to be. But it couldn't hurt because we know. So choose that to be that, and therefore f of nx minus f of x is less than epsilon for all n greater than or equal to n, and x in minus a half. I don't see why that's a problem.
Yeah, it's not. That's the definition of uniform.
Yeah. I don't see why that's a problem. Seems okay to me. His solution is different. You can go and look up his.
That was my solution. Looked at it.
Yeah.
His solutions are different again.
Yeah. There are multiple solutions because you could go right back to the beginning and go, well, the distance between these things is this, and if I choose n to be big enough, it'll work. Is that's what you did?
What he did was, because it was a decreasing function on 0 to a half, he chose a half and subbed it in, so that was the maximum, and then he just solved it to show the n. So everything, and since it's
Just
symmetric,
the way it comes out.
yeah.
So he's probably thinking in his head that picture then.
It's not the same way as this.
Probably.
Yeah. Just
So this picture here is saying, like, if you're at a half here, then it does go down. So yeah.
Anything less than a half.
So technically, you don't need a half. It could be from minus. As long as it stops before you get to 1, you'll be good. All right. I'm good for another 20 minutes. That was grueling. I'm sorry. You've all been warned before that it's not my job to help you with these secondary courses, so you take them what you get. Someone was talking about something in whispers back there before. Is it still relevant?
Oh, just back and forth.
Past exam question or something that's like a bit curly or...
If you make up a series and try and converge it, show how to converge it.
Just converge it. Step 1, converge it.
Keep going.
I've got one that's pretty similar to that, but it's different.
All right.
Question. It's just an actually structured question.
Which one? Oh, the whole thing?
Well, the first part's just the definitions, and then
Okay.
it's, B is to show that it's converging, and then
I don't think we've before. The test is so bad. My assignment so bad. I was in 90%, and I think I failed that test. So it brought me down to like 6.
Okay, so if you converge uniformly, you have to converge pointwise, right?
Yes.
Yep. Okay. So the exam question says, show that this sequence converges uniformly to this function, and does it converge pointwise? So if part I is true and it does converge uniformly, the answer to part 2 is yes. Yeah, that's good. All good with that. Okay.
I think pointwise might be an alternative to uniform.
No, well, we looked at this the other day, didn't we? On a bounded interval, converging pointwise is the same as converging uniformly. Closed and bounded interval. On a closed bounded interval, sorry? Yeah. So on a closed bounded interval, converging uniformly is the same as converging pointwise, and they're not different from each other.
But is it bounded?
But this is not bounded,
Yeah.
and that actually should be a round bracket. But on an unbounded or open interval, or on an unbounded or open interval, or both, they might not be the same. But if you converge uniformly, you must converge pointwise. So all Dalmatians are dogs, but not necessarily all dogs are Dalmatians. Okay. But given particular information about the dogs, they all are Dalmatians. Not even all dogs occurring in 101 Dalmatians are Dalmatians.
No, they died a couple after this.
Oh, don't tell me that.
I just watched the car.
You know, all the Dalmatians are Dalmatians. Okay, moving on. So we're supposed to show it's converging,
Sorry.
converges uniformly. Well, it can't hurt to draw a picture of this. Okay, so we do have the function we're aiming for. I can draw that certainly. And when n is 1, I've got x e to the minus x. It's going to be generally decreasing, right? So it's going to have like something like that. And then when n is when n is 2, I get 2x e to the minus 4x. So the negative power up there in the e to the x is even bigger, and so therefore it goes even quicker. So it's going to have sort of like a, yeah, it's going to, something like that, I'd say. Could be wrong, but roughly. Okay? So more and more of it will be close to 0, I'd say.
What was the function again, sorry?
nx e to the minus n squared. So the derivative of that, I have to use the product rule and I don't care to do that, but e to the minus x decreases faster than any polynomial increases, and so it does have that tail that goes down. But e to the minus 4x decreases even faster than e to the minus x, and e to the minus 16, 16 and 25 and 81x, they all decrease even faster than the one before. So it should be, the higher that n is, the quicker the decrease will wipe out the x, and so it should have its turning point earlier and earlier. Its turning point might even be higher over, but I've got the right idea for my picture. Okay, and that's why it converges uniformly, because it should be possible, because my height will decrease to pick and given any epsilon, it should be possible to choose an n so that that maximum is as low as it needs to be. And that sounds to me like a really good idea. Find the maximum of this function and show that the maximum of that function is less than, if n is big enough, it's less than the epsilon I want. So based on my picture, that sounds like the best approach. That's what I'm going to do. Okay, so
The biggest possible thing, and then if it's not in that.
I'm just going to differentiate it.
I can differentiate.
Also helps if there's no x in there. There's no x in there.
Yeah.
Basically, I just play around trying to get something like that.
That's what I get. So I differentiated here using the product rule. So I kept the nx and I differentiated the e to the minus n squared x. I differentiated the nx and kept the other one, and then they've both got an n and an e to the minus n squared, so I pulled that at the front and I got this. And that's a plus 1 there, by the way. And that is 0 when x is like 1 over n squared. Yep. And that's the only place. So, one over n squared, because I basically set that equal to 0. And so the maximum is f of 1 over n squared, which is n times 1 over n squared e to the minus over ne. awesome, because that's e to the minus 1, you see. Alright, which decreases as n increases. So, now let's see if we've got this right. So let's just talk this through. We've just done some preliminary work. We have to use the proper definition. So the proper definition says, given an epsilon, I can find a capital N, blah, blah, blah. So let epsilon be greater than 0. The distance between fnx and fx is equal to the distance between fnx and 0. Right? Which is less than or equal to 1 over ne, right? Which approaches 0 as n goes to infinity, and so therefore there must be a capital N that's less than epsilon. So therefore...
It doesn't depend on it.
Yeah. There is an N such that
It took me ages to figure this stuff out.
N greater than or equal to N. And note that since this doesn't involve an X, it's the same for all the X's. Right, you'd like to hope that he gives you something like that. But we have a good strategy that if you can guarantee that your function has all functions have a maximum, and those maximums are decreasing across the functions, then it'll in that domain, then it'll work. And the nice thing about the other function that wasn't convergent in the assignment, uniformly convergent, was because it had that point. They all had to be equal to a half somewhere, and so they didn't have that minimum that they could get below. Yeah. They didn't have a decreasing maximum, they all had the same maximum. Roughly. Okay. Right. That was easy. Relatively. And this argument seems to be something he accepts because he writes it in his own assignment solutions. But to be fair, you should probably have said, well, why don't we choose n to be epsilon be we want an epsilon up here to be like epsilon on e or something, e on 1 on e epsilon. So you could have done that too. So you could have done like or choose n equals 1 on epsilon e or something, and then fnx minus fx is less than or equal to 1 over e on epsilon e, which is e on epsilon e, which is epsilon. Woohoo! And we're done. Okay, so you could do it that way too. So you are allowed to. But he's used these arguments with the approaches himself, so it's all just, that's okay. If you can't begrudge, he can't say you can't do that if he does it himself. And he's an eminently reasonable person, isn't he? Those listening, suppose that you're in 2014, hello future students, and your lecturer isn't Nick Bookdale, well, you'll have to figure that out for yourself. But usually people lecture it for 3 years in a row, so we've got a couple of years to go. So if you're listening to this, and this video is still here in 2017, you're stuffed. Anyway, I'll probably do a new one by then. Okay, anything else? Just some random proof. Do you have one?
Cauchy's mean value theorem.
Okay, is that the one we've got two functions? And we have how to use the ordinary mean value theorem to prove it?
You can use roll language.
Yeah, you use roll language was special. You set it up. If you set it up rightly, then it all falls out.
Yeah.
needs to set it up.
You just have to pick the right function to apply
Yeah.
rolling.
Yeah.
That's how we did it in the truth.
Yeah, and
It's
that's
all
all
just
it's
set
done.
up.
And I don't think guessing is involved. It's like, oh yeah, it's
That looks kind of
Cauchy's mean value theorem says that you've got two functions, right? So you've got like f sends AB to R, and G also sends AB to R, and then it says therefore there exists, and they're both differentiable.
And G doesn't equal 0.
It's not equal to itself at both ends. Yeah,
Yep.
we'll put that in a minute. But
Equal 0.
there
G's
exists,
not allowed to be 0 for
and G dashed isn't allowed to be 0, and yeah, there exists a C in the open interval AB with like f of B minus f of A over G of B minus G of A equals f dash C over G dash C. Is that it? Okay, so f of B is not allowed to be equal to G of A. That G of B is not allowed to be equal to G of A, and G dash C is not allowed to be 0 at any point. Actually, that's probably okay. You don't need to worry about that, because as long as it's not 0 at that spot, you'll be fine.
Yeah, which is what we said, because the other side is taken care of by roller. So
Okay.
we know that that's not the case or something.
So, we have two theorems. Well, we have several theorems that talk about the existence of a C between 2 points, most of those theorems are proved by reference to Rolle's theorem. So it seems reasonable to use Rolle's theorem. And Rolle's theorem says that if there is some function that's equal at 2 points, then its derivative must be 0 somewhere in between. So we want a statement that involves a single function whose, when its derivative is 0, we can rearrange it to produce this. So we should do a little bit of working on our bit of side paper, on our scrap paper. On our scrap paper, we say, well, this would have come about by setting some function equal to 0 at the point C, the derivative of some function. So if I can rearrange this so that it happens to be the derivative of something, so it seems reasonable that I should do this. So just, multiply both sides by G dash C and both sides by G of B minus G of A. And then put them both on the same side. Sounds like a plan. So I'm basically working backwards here. If I had some foresight, I probably would have just worked backwards from the bottom of the page up. So this would be the derivative of g of x times f of b minus f of a and f of x times g of b minus g of a at the point C. Now I just need to be sure that that function, okay, I'll think about that. I just need to be sure that whatever function I differentiate, so let's just think about this. So this would be the derivative of g of okay, so that would be my h of x. So when I differentiate it and sub in C, I get that. So let's just check. We need this to be equal to 0 or equal to itself at both A and B. So if I sub in g of x, if I sub in x equals A, it's totally not going to work. If I sub in x equals A, that's not going to work, is it? Is it? If I sub in x equals A, I've got g of A, b of A, and that's, I've got g of A, f of A here, and a plus g of A, f of A here. I've got g of A, f of B, and f of A, g of B here. Okay, that's okay, because when I sub in B, I'm actually just going to do it and see what I get. So we've got G of A, F of A, and F of A, G of A, and that's negative and that's positive there, so they'll cancel each other out. G of A, F of B, and F of A, G of B. Okay. And what happens when I sub in the other end? H of B will be G of B, F of B minus F of A, minus F of B, G of B minus G of A. So G of B, F of B, and I've got a minus G of B, F of B, so they cancel each other out. I've got minus G of B, F of A, and plus F of B, G of A. So they're equal to each other, A and B. Rolle's theorem will work. Cool, I have basically done the reverse of what I needed. Okay, so now that I've done that, I can now say let H of X be equal to G of X times F of B minus F of A minus F of X times G of B minus G of A. H of A equals blah 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 equals G of A, F of B minus F of A, G of B. H of B equals, and do a bit of working there, G of A, F of B minus F of A, G of B, which is equal to H of A. So therefore by Rolle, there exists a C in AB with H dash C equals 0. So H dash C, H dash X is G dash X, F of B minus, F of A minus F of dash X, G of B minus G of A. So H dash C equals that with C in it. Which is equal to 0, and you rearrange, do some working, and you get what you want. So you would, in the exam, actually put the working in.
Oh, can't we scribble? Oh.
Yeah, insert working here.
Project to lecture, whatever.
If I can't do a question, I'll write that.
So I say I scribble by the answer.
Yeah.
Step 3 under
No, on the first page of your exam book. No, scribble means insert working here.
Insert your thoughts.
Exercise for the reader. That would so not fly in the exam, but I would love to see someone with the balls to try.
Well, then if I figure I'm going to fail it halfway through, I'll give it.
It'll give him a laugh.
Good line question.
Yeah. So the key to a lot of these things is actually working backwards to try and figure out what the function was. Some of them have to be a bit creative because I was just wondering if I might need, back at this stage here, to actually have like g of x minus something, so that when it differentiated the g of x minus something, that was a constant, so that when it differentiated the constant went away. I didn't know if I was going to need that until I subbed it in to see what it came out to be. So if these didn't come out the same, I'll need to sort of adjust this bit here next to the g of x so that when I did sub in the original things, they did come out to be the same. So yeah, because you can imagine that if I had like g of x minus g of a or something, the minus g of a part would have disappeared when I differentiated. And so I would still have the same part up after I've done Rolle's theorem. You just need to be careful because the function being equal to itself is based on the original function, not on the derivative. So sometimes you have to adjust it a little bit. But sure, not bad enough. All right. Well, that's probably quite enough for today. I'm a bit tired. Your exam's only 2 hours long, so you shouldn't practice. Is it 3? Oh, really?
2 hour exam.
Ah, you've got 3 hours to do it. Oh yes, I remember someone being rather upset at that.
It's everybody tough luck.
Sorry?
It's a tough luck. We love it.
He just forgot.
Just
Nothing like asking for forgiveness rather than permission.
The real analysis